Okay, hi everyone, and welcome to our third class. Now, in the previous one, we talked about controlling the electrical stress in different parts of the power system assets. So that stage happens usually at the design stage. You want to make sure that there is no areas in the equipment that you have that has high stress that might lead to partial discharge and eventually to failure of the asset. Now, once you design the asset, now I'm only talking about the design from the electrical stress or the high voltage perspective. There are, of course, other aspects as well. Now, you have to test the asset to meet the design criteria that you have. And again, I'm talking about here testing the asset from the high voltage again, because there are different tests each asset go through. But one of the classes of the tests is the high voltage test to test the integrity of the insulation of your equipment. So basically, testing is extremely important that you have to do it. Okay, and the you have to, for example, ensure that your equipment is free from partial discharge, or the insulation is good enough to withstand the high voltage and it will not fail in the site. Also, now when we need to do the high voltage testing, okay, we do it at different stages. For example, when you are developing a new product, you need to do that. When you do modifications in your existing design, you have to do the testing as well. When you manufacture it, before it leaves your premises, you have to test it at certain high voltage tests. So that is a requirement. Some of those tests are routine tests, some of them are type tests, some of them are special tests. But you need these tests before you deliver your assets to the customer. Some of the tests before commissioning. Sometimes you have a fault in the asset, you do some repair. You want to make sure that the repair is okay, then you have to test the asset as well. Now, the testing is done according to different standards, depends where do you live. Okay, so for example, in the Middle East, in India, in Pakistan, in that part of the world, in Europe as well, the IEC standard is the main standard there. It's more of an international type of standard. In North America, we have the ANSI standard. There are similarities and differences. I have seen many tests specifications for the same asset. You will see some differences between the IEC and the ANSI. When we start talking about the testing of the assets, I might refer to some of those differences. Now, this is for the Canadian standard, British standard, and so on and so forth. Some countries take those standards and modify them a little bit, and they make them as per their standards. So now, when it comes to the high voltage testing, we test the equipment, depends on its usage, of course, but these are the general types of supplies needed or tests needed for the asset. The first one is the AC test. So basically, it's a sinusoidal test, high voltage test. Okay, it happens most of the time at the power frequency, so it's either at 50 or 60 hertz, the same frequency we have in our network. Or sometimes we have it at a very low frequency, and we'll talk about it a little bit today, but with more details as we give examples of the assets. DC supplies, this is another type of test that we do, and we need to understand the performance of the supplies. And finally, the impulse testing, we test for lightning, switching, and steep front. So the objective of our today's lecture, we will not talk about the tests. Tests will be done later on when we give some examples of the assets. But our main focus today about the design of the supplies that deliver us these voltages. So we talk about how we design an AC supply to do the high voltage AC tests, how we design the DC supply, what are the design parameters, and finally, how we design the impulse generator to do impulse test. So we'll start with the power frequency AC supply. Now, because most of our assets are connected under AC systems, so they have to be tested under AC power frequency. Okay, now these are some of the requirements of the power supply that we have to use. So basically, wave shape, it has to be very much sinusoidal and almost distorted. There is no distortion in the signals. So for that, we use some line filters to remove any of the high frequency that they might have. The peak value of the AC supply is √2 times VRMS within plus minus 5%. So this is some tolerance available in the standards. So we expect to have more deviations when we use, especially when we use nonlinear loads. Usually, or most of the time, the test done at the power frequency, which is the 50 or the 60 hertz. But there are certain exceptions. We might do the test at multiple of those frequencies, and we will give an example later on when we talk about transformer testing, or when we test it at a much lower frequency. And today we'll talk about it a little bit, but later on we'll talk about it in details when we talk about testing of cables. Okay, so now what is our assets? What we are testing basically? Now we are testing the insulation. So regardless of the test that you are using, basically you are applying the high voltage between an electrode and a ground. So you are testing the insulation in between. Okay, so we are not interested in testing the magnetic material or testing the conductor. We are interested in only testing the insulation material. And when we say insulation materials, it means that it's the capacitance of your assets. That is the one that will receive the current. So we look to the asset as a capacitor. So if we talk about cable, the cable, when we model the cable, it depends what type of studies you are working. We can model the cable as a resistance in series with inductance, but that is if you are interested in to see the power loss in the cables, and you want to see what is the copper loss if it's subjected to full load or half the load. So that's a different test. Our interest is to see if I apply a high voltage between the core of the cable and the shield, can withstand the high voltage or not. So I'm testing the insulation. Insulation means it is the asset, the way we look to it, the asset as a capacitor. So these are some typical values. It's very important to know the capacitance value of the asset that you are testing, because you want to see what is the loading effect, how much current it will take from your supply. Can your supply provide this current or not? So we have to know the capacitance, and these are some typical values. For example, simple post or suspension insulators is around 10 picofarad. If you talk about bushings, it's a bit higher. Potential transformers, 200 to 500 picofarad. If you talk about power transformer, it can go up to 10,000 picofarad. So when you want to do the testing, especially, for example, we test an impulse test, and we'll talk about that later on. The impedance of the load, it will impact the wave shape that you are applying. So you have to understand, you have to know how much loading effect, how much capacitance is your assets. For cables, usually we assign or represent their capacitance per unit length. For every meter, how much is the capacitance? Because we take samples of the cable, and knowing the length of the cable, we'll know what is the total capacitance. Okay, now the design of a 50-60 hertz test transformer. So these are the transformer that we use them to test the asset, is not big difference from the regular transformer. Before we go in details here, let me explain to you a little bit about how we design the actual transformer, the single-phase transformer or three-phase transformer. What is the design for that, to see the difference between the conventional transformers and the high voltage testing transformer. So the first thing that you do when you design a transformer, the first formula we use this formula. The voltage per turn of the transformer is equal to 4.44 times the frequency times the flux density times the area, the cross-section area of the core. Now, how from where this comes, I will share with you after the class a video that shows to you from where we get this 4.44 and how we got this, how this formula. So basically, we start with this. Now, the voltage per turn at both the high voltage and the low voltage side of the transformer. Okay, so we use the same voltage per turn, and we know some typical values from our experience. So we use certain values for this as a one parameter, voltage per turn. Okay, equal to 4.44, a constant. The frequency is constant. It's either 50 or 60 hertz. Okay. Now we have these two parameters that decide the size of the transformer and the cost of the transformer, the flux density and the cross-section area of the core. So what we try to do in regular transformers, now we have what we call the BH curve. The BH curve is something like this. This is the H, and this is the B, the flux density. So we try to design the transformer at saturation level. So we go try to, which is around 1.8 to 2.0 Tesla. So we try to push the transformer to go to a bit of saturation. Okay. Why? So I want to increase this as much as I can because I want to reduce A. Because as I said, we start with a given value based on the insulation strength that we have, especially at the high voltage side. I select a value, voltage per turn. What is the voltage I apply between turn to turn? That is how much I start my design with. Okay, these two are constants, so I have these two parameters to play with. I want to reduce the cost of the transformer. This is the cross-sectional area of the core. So I want to reduce this because if I reduce the core, I will reduce the size of the winding, I will reduce the tank, the oil, everything will be reduced. How to do that? I push the flux density to be as high as possible. And then from there, once we decide the cross-section area of the core, now I know the voltage per turn, then I know how much high voltage, let's say the voltage was 11 kilovolt, okay? Then I will know the number of turns. And for the low voltage, if this, let's say 400 volt, then I will know the number of turns. So now I know how many turns, what is the cross-section area of the core, then here we start that design of the transformer. Now, when we design the transformer like this, with this criteria, which is reducing the cost, and we are going very close to the saturation level, and actually we are starting the saturation level, we will have what we call the no-load current of the transformer full of harmonics. Okay, we have something called the no-load harmonics or no-load current of the transformer, and that current is basically the energizing current, the current that will set the flux in the core of the transformer. So basically, if I have a transformer like this, so this is your primary voltage, okay, and here it is your secondary voltage, and this is open circuit. I do not connect anything here. So the current that we call it the no-load current. Now this current will be highly distorted, and that will affect the waveforms of the supplies. We don't want to have this at the testing transformer. The reason I showed you all of this is just to tell you that in transformer design, when we design it for testing, we don't want to go too deep to saturation. We don't want to have a harmonics. We want to have a sinusoidal currents and voltages. So that is the criteria we have it, and this will lead to the following points here. Now let's go back here to our presentation, and here comes. So the first point that when we design the transformers in testing, the kVA rating is much less. Why? What is the kVA, which is S, is equal to, as a magnitude, let's say voltage times the current I. Okay. Now the current that we be using in the regular transformer is extremely high. This is the load current. The current that we use in high voltage testing is the current that go through the insulation. Extremely small current. So the kVA rating of the transformers in a testing transformer is much less. The second point is the flux density. That is the point I was referring to when you're talking about the design of the transformer. We have much smaller flux density because we want to work in the linear region. We don't want to go to deep saturation, so that we don't want to have any distortion in our current. Okay, so that is a very important criteria in a testing transformer. A big difference between regular transformer and testing transformers. Okay, now regular transformers, we have them outside under weather conditions. So there will be pollution accumulated on the bushing. And once you start to have pollution with some wetting conditions, you will start to have arcing on the surface. So we increase the creepage distance of the bushing. We'll talk about bushings and their design and testing later on. Okay, but now the testing transformer is not meant to be outside. It is inside the lab. So there's no pollution. So I don't need to have this high creepage distance. As a matter of fact, you will see that some transformers, they don't have even bushing. There's a certain arrangement for the high voltage testing because I don't need to have this creepage distance for those high voltage testing transformers. Okay. Second thing, that also these transformers are not supposed to be subjected to switching or lightning conditions like the regular one. So I don't need to pay attention to transients, over stresses when we design those transformers. Now, when we design the transformer 100 kilovolt or below, we use dry type or filled with SF gas. So if the voltage that we use, now we consider only about the voltage because the power rating is extremely small. So it's either dry type or filled with SF6 because there's not much of cooling needed for when you have such relatively low high voltage. But if it is from 3 to 500 kilovolt, usually we use oil-filled transformer for the cooling purposes. Now, when you apply the voltage, there will be some arcing sometimes. Sometimes you do testing for flashover tests. So during the test, you have to maintain that the voltage within 3% during the transient currents. Okay, so that because once you start to take current from the transformer, there will be a voltage drop inside the transformer. The voltage that you see it at the terminal will be this. Is the voltage that you are producing minus the voltage drop. So the transformers are designed that whenever there is arcing, that the drop will be minimum. Now, some of those transformers are meant to stress the asset at high voltage so that measure partial discharge. So there are different type of tests can be conducted to generate stress on the insulation and see how much PD level it can produce. Now, when you use this transformer for that specific application, you want to make sure that the transformers are PD free. It doesn't make sense that you have a transformer that's not PD free and use it to test an acid, and then you start to measure PD, partial discharge coming, and you don't know if it's coming from the acid or coming from the transformer. So those transformers are usually guaranteed that at the rated voltage level, they have less than 5 picocoulomb, or sometimes less than 5 picocoulomb when they are stressed at their rated value. So these are some criteria about the design of the AC high voltage transformers. Now, how they look like, this is one example, and this is the most common example. We have two examples here at the high voltage lab at the University of Waterloo. I am planning to make a video about these transformers. I will go to the lab and make a video and share it with you later on. And we have two transformers at the University of Waterloo. We have 400 kilovolt and 150 kilovolt, and this is how they look like. So what is this exactly? What is inside? If you come here and look, this is the core. This is the core of your transformer. Okay, this is your low voltage. So number 2 is your primary or the low voltage. This is where you excite the transformer. Here you apply your low voltage to get the high voltage. So this is your low voltage, and the outside winding is your high voltage. So this is like a cross-section area, as if you are coming here and you slice the transformer. Okay. So these are the basic three components: high voltage, low voltage, and the core. From where we get the high voltage? From here. Yes. It's like a big donut here up there. This is your high voltage. There's no pushing here in that type of design. I said that is the most common design for high voltage high voltage testing transformer. Of course, there is the bushing one. I will show to you also how it look like. So this is the high voltage. Here is the connection between the high voltage to the outside terminal. So this is your high voltage is coming from here. Now this red color that you see here is basically, this is number 7. Number 7 is an insulated shell or tank. So here we have an insulated tank. This is not high. This is not basically grounded. No, it is just an insulating material, and this will allow you to apply high voltage, because this is, you can see here, if this is grounded touching the high voltage, you have a big problem. Okay, so now you are insulating the high voltage. This is the ground. The ground is the bottom level. This is the ground. Here is the ground, and here is the high voltage. Okay, so this is basically to insulate between the high voltage to the ground of the transformer. So that is the most common type of transformer used for high voltage testing. Also, we have the bushing type transformer. This is also a testing transformer, but these are, I would say, more of all types of design. The recent ones is the one that I have shown to you. So they are different. They are very, very similar to the previous one from the inside. The only difference is the bushing here. You can see the bushing here. And you can see here, this is the condenser. It's a condenser type of bushing to control the electrical stress inside the bushings. Okay. Now, these transformers usually 300 kilovolt, maybe 400 kilovolt. That's it. What if I need high voltage more than that? Okay. Then we will go to another concept to be able to do that. Okay, so for 300 or we have here 400 kilovolt at our lab single unit. Okay, that's okay. Like, but when you start, but it was really a nightmare to ship the transformer to the lab, install it in the lab, make it enter from the doors. It was a big problem to be able to move the transformer inside the lab. Imagine if it is like 1 million volt, and sometimes you need it. It depends how you test an asset that is working in 700 kilovolt. So you will test it more than 1 million volt. So you need a transformer that supply much higher voltages. How we can do that? That now becomes very costly, and you will have too many installation problems. Plus, as I said, the transportation, energizing becomes even more and more difficult. Remember, those transformers are manufactured somewhere else than here. And you have to transport them and you have to install them. So that is really costly and becomes very problematic when you work with these extremely high voltages. Now, how we can get rid of these drawbacks, these problems? Basically, we use a series connection, or what we call it cascading transformer. So we cascade transformers in series. So each transformer will having, let's say, certain voltage, let's say 200 kilovolt. We will connect the high voltages of those transformers in series. Then you will be adding the voltages. So if one transformer provides you with 100 kilovolt, if you have 3 transformers, you will get 300 kilovolt. Or if each one can supply 200 kilovolt, if you have 3 of those transformers, then you get 600 kilovolt. As we will see how we will do this cascading business. So this is 3 transformers cascaded together. In the next slide, we'll see physically how this looks like. But now let's look from the schematic. Now we have transformer 1, transformer 2, and transformer 3. Each transformer will have 3 windings. The first winding is called the primary winding. So this is the primary, this is number 1. This is the primary winding of the first transformer. This is the primary winding of the second transformer, and this is the primary winding of the third transformer. And we have the secondary winding, number 2. So this is the secondary winding of the first transformer. This is the secondary winding of the second transformer, and this is the secondary winding of the third transformer. No, now these three transformers are identical. Okay, so are the same, except for one issue. I will talk about it in a few minutes. So you energize the transformer from here, you are getting this voltage. So you get V out of it. Now, it doesn't matter what is this V. The other transformer will give you also V, but because the secondary of the second transformer and the secondary of the first transformer, they are in series, as you can see here, they are basically in series. If they are in series, the voltages that you are getting, you are just adding. This will get you 1V, this is another V, then you will get 2V. Okay? The third transformer, same thing here. So you have here another V here. So this is also connected in series with these transformers. So we'll have 1V, 2V, and this is your output will be equal to 3V. Now, how we can do the induction between the transformer 1 and the second transformer? We have the tertiary winding, so which is number 3. So this is your tertiary winding here, here, and there. This is your tertiary winding. So this is the objective of this, is to induce the voltage from stage 1 to stage 2, stage 2 to stage 3. So this will be connected to the primary of the other transformer. So it will convert part of the voltage in the secondary here, connected to the primary of that transformer to energize the coming transformer, and so on and so on and so forth. Okay, so that is overall the three transformers. Okay, now what is this 3P, 2P, and P here? Okay, now every transformer will have certain loading. Okay, so when you connect and let's say you are testing here, you are connecting your load here. This is your load here. Okay, so it will have certain current, will absorb certain current I. Now, this transformer will be supplying that current. But this transformer, it needs to supply the current to both, for the transformer and for the load. This is what calls 2P. It has double the load. Third one, it has 3 loads. So it has to supply the load and through the other 2 transformer. So the other transformer is considered as a load for it. So the power rating of the first transformer has to be 3 times the first, second, and which is again in turns double the rating power of the third transformer. But other than that, it's all exactly the same. So how they look like here? So this is the first transformer. This is this transformer, the first one here. Okay, and it is connected. The primary will be applied here. Okay. Now, what you can see here, the high voltage from this transformer is connected to the tank. So the tank itself, basically here, it will be, you are raising the high voltage of the tank. This is why the tank has to be insulated. These are insulation. This is connected to the ground. So here, this is 0 voltage. And you see that here, that these transformers are grounded here. But those transformers, they are not grounded. Okay, because you are alleviating the voltage here to this voltage level. Okay, and further when you this now, so here from here to the ground you have only your V voltage here. Now from here to here, this transformer will provide you with V, and the tank is energized by the other transformer, another V. So you have from here to here V, and from here to here another V. So total you have 2V. Again, you raise the voltage for the tank here to 2V here. So from here to the tank is V. So each transformer will give you only V. Every transformer will give you only V. But then from here to there, it is 2V. So it becomes, the total output here becomes equal to 3V. So this is the idea of the cascade transformer. So each transformer, this is one of the advantages. You see, look to that transformer now. Forget about the installation. They are identical. Okay, so that will make the cost lower. because you are cascading exactly the same units. The disadvantage that the primary current for the lower unit is higher than the single phase transformer. So sometimes we design all transformers with exactly the same rating, which is the first transformer. So we are over designing. So that's a cost that you need to pay. Or this is the disadvantage of having the cascaded transformers. Now, these transformer, either the cascaded or the previous one, we use them under lab conditions. Now imagine, and this happens a lot, I need to do high voltage testing in the field. Okay? Of course, I cannot take with me something like this to the field. This is impossible. So I need to have something that doesn't have that huge weight, and I can at the same time use them in the field. Okay, because the weight is very. I mean, you cannot move those transformers, and also the power requirements. It's not really possible. Another problem with those transformers in the field is that there could be sometimes possible resonance at 60 hertz. But remember, we are testing capacitive loads. This is what we're exactly testing. So this is the capacitor, and there is an inductance in the system. So there's a possibility that you will have a resonance. If you end up having a resonance, then you will have a significant overvoltage that is not intended. Okay, so that can damage even the equipment or damage the transformer itself. Also, you might have resonance, maybe not at the fundamental, but at the harmonics, especially the third harmonic. Yes, we try to minimize the harmonics, but you could have a little bit of harmonics. So it could happen that you have an over voltage happened at other frequency than the fundamental one. So how to solve this issue? We use what we call the resonance transformer. So the resonance transformer, yes, you might see them sometimes in some high voltage labs. I have seen one of those transformers, if I recall correctly, at Kinetrix, the high voltage lab in Ontario. But also, these are mainly intended to be used in the field. So basically, that is a resonance transformer. What do we have here? This is where you have your inputs here. This is like a regulator here. So here you step up the transformer here. This is your output. Now this is your testing object. So this is your tested object. This is where whatever you are testing. Okay, could be anything, but as I said, we look to it as a capacitor. Okay. Now we have a variable reactor, something that we control. Yeah. Okay. So we try to change the inductance to be in resonance with the C. So the capacitance of your system will be, or your equipment to be tested will be cancelled with the inductance of this variable inductor or variable reactor that you control that. So now you are completely you are removing the loading effect. The only effect now is the internal resistance of your transformer. So that will result in extremely very high voltage and very low current requirements, as we would see. Okay? So the main formula that we have, that the power, this is the P actually, the input power is equal to the Q output divide something we call the quality factor, Q. Q is the quality factor of your resonance circuit. Now, the quality factor, generally speaking, is equal to the energy stored over energy dissipated. Okay, so this is the definition of the quality factor. Okay, so the energy that you store is the kVAR. This is how much Q you are supplying. Remember, our system is a capacitance, so you are supplying to it a kVAR, but you are consuming a power. This is the power that you are consuming. So when you have very high Q, usually 50, quality factor is high for those transformers, then basically you are minimizing the input. the amount of power in the input. And remember, the power here is the voltage times the I. So if I basically V is, this is something that you can't change. So you are reducing I. When I reduce the I reduce the whole size of my equipment and make it very easy to be used in the field. So at resonance, your I, the current equal to the excitation voltage divided by the internal resistance that you will have in your system. And your output, the output voltage equal to the Q factor times the excitation voltages. And as I always say to the students that in any passive circuit, your output is always less than input. Always. Unless you have an active circuit, always your output is less than input, except for a circuit at resonance. At resonance, your output voltage is higher than your input. So this is ideal, especially for testing cables, because cables they have very high capacitance, okay, and you want to cancel their impact to reduce actually the size of the equipment. What are the advantages of series resonant test transformers? It has certain advantages. First of all, now I am controlling the resonance. It's intentionally done, so it is controlled. That will eliminate unwanted resonance. Now I am the one who is controlling this. I'm going to the resonance at that specific frequency, okay, to get high voltage, to reduce the size of the equipment. So it's unlikely that you will have a resonance at a different frequency. Okay. Second thing is the output voltage is directly proportional to the Q, which is typically 50. So we are getting extremely high voltage coming out of those resonance frequency with a smaller size. The voltage waveform is also improved because we're eliminating the harmonics. And as I said, that will result in we have a relatively small and light unit that can be used in the field. The final thing that we'll talk about it here about AC. This is the last thing I will talk about it here for AC, which is the very low frequency testing. So those are devices that this is a new trend. Of course, when I say new here, I'm talking about relatively new because high voltage area is somehow an outdated area. But now there are certain new things in high voltage. When I say outdated, I mean that in the 40s, in the 50s, in the 60s, that is where the main engineering and science about high voltage has been developed. The mechanism of arcing, developing new materials, the whole world was working in that area. After that, there is sort of a steady state now in terms of development. Okay, so most of the things that we talk about it today, this is the understanding of the 50s and the 60s. Now there are certain new trends coming. One of them, the new trends, is the condition monitoring of the assets in the field. That is extremely important aspect. Why? Because many assets have exceeded their life expectation now. And we need to know, we need to assess those assets. So we need to come up with different techniques that are representative of the stress that the equipment might have. We don't want to have an extra exaggerated stress, okay? We want to have an stress that really represent the, the actual stress in the field, not too much. And this will lead to development of new different test methods, test equipment, and so on and so forth. One of them relatively new is the very low frequency, which is it's a sinusoidal that goes between 0.01 to 2.1 hertz. Now, there are different shapes, but the most common one is the sinusoidal that okay, represent actually the real voltage that we applied in the field. Now we use this one whenever we need to do an AC testing for high capacitance load. For example, long cables, and I will give an example why this is extremely important. Now, trend, I would say 10, 15 years ago, if you want to test cables in the site, people use DC. Okay? It has been found that when you use DC in the site, failures happen more frequently for aged cables. And those aged cables, they are not bad to fail in the test, but the test is severe, much more severe than the stress that those cables are seeing, because the cables are actually energized under AC. Let me explain this is a little bit. So let me go a little bit out now. Let me go back here to my note here and explain this to you. What do we mean by this? So when you have look cross-section area of the cable, this is your high voltage here in the middle of the conductor, and outside you have the grounded shield. This is grounded. Okay. Now, when you apply AC voltage, this is the actual test. So this is a plus, this is minus. Okay. Now, every time you are basically reversing the polarity, the space charge, we call the space charge, it neutralizes itself. There's no developed space charge between the high voltage electrode and the ground. But when you use DC only, one polarity, after stress, you will have here a space charge developed between the high voltage and the ground. And that space charge will create a very high electrical stress that does not exist in the field. Okay, so this is a big problem. Okay, because I am overstressing the acid, especially when the acids are aged, not new acids, and they are failing not because they are bad, but because the test is actually very severe for them. So that is an issue. And this is why people do use the resonance transformer, because the resonance transformer basically supply you with an AC voltage. So it is more of actual type of type of stress. However, again, sometimes the size of the resonance transformers for cables becomes too much. And this is why they come out for the low frequency. And let me give you some numerical example. The XC, the capacitive reactance of the capacitor, is equal to 1 over 2 pi FC. So at 15 kilovolt, if you want to test cable, distribution cable in the field, if this is 60 hertz, and this will be like around 1 microfarad, okay? Then the capacitive reactance is 2,650 ohm. So that is your XC in ohms is equal to 2,650 ohms. Now, if we apply, when we stress those cables, we need to stress them higher than the rated voltage. So according to the IEEE, we need to stress them at around 22 kilovolt. So that is the voltage. This is the impedance. So we need to supply an 8.3 amps. Simple Ohm's law, V over I. Okay. So you will have to have an 8.3 amps, which is a rating, the rating of the equipment. To be able to supply this, you multiply V times I. This is your S, which is equal to 22 kilovolt times 8.3. That is a huge 183 kVA. Your supply will be very high. I can have such supply in the lab, but not in the field, because how to move that? Now, let's see if we test that at 0.1 hertz. Now, 0.1 hertz is still AC, so there is no space charge. It is slower than the 60 hertz, yes, but it is basically not DC. So the stress more closer to the AC, not the DC. Now, because of the very low frequency, the impedance or the reactance of the capacitor becomes extremely high, 1.6 mega ohm compared to 2.6 kilo ohm. So the current becomes very small, 14 milliamps. That is how much power needed from your device, which will make the size, instead of the 183 kVA, it's a fraction of a kVA. So it is like 600 times less than the power rating that you need to use. Okay, and that is why it is preferable or this is one of the new trends in testing the cable, is to use this low frequency. Any questions so far before we move to the second one? We'll take the break in the middle of the DC when we have like around halfway through. Okay, so it seems everything is okay. Now let's go and see the DC stress. Okay. Now, there is a growing interest to have the grid have DC part. Okay, if you go back to history, there was a big war between Tesla and Edison. Tesla was promoting the AC system, Edison the DC system, and the war, we call it the war of the current. In history, this is known as the war of the current. Tesla, because once we start to need to send too much amount of power, you have to raise the voltage. You cannot do that in DC. So the AC system prevailed since then. But with the improvement in the power electronics, we can still generate the voltage in AC, step it up in AC, then convert that to DC. Then transmit the power in DC. Once we reach the load, using an inverter, go back to the AC system. Now, the cost of the system is higher as a starting infrastructure. So if you look to this curve, this is the cost, the y-axis, and the x-axis is the transmission link. So to start with, this is the cost, the DC terminal cost, and here is the AC terminal cost. So the AC is much, much less. Okay. Now, as you start to send the power for longer distance, the DC cost is, the slope of the DC cost is lower. Why is that? Because in DC, there is no reactive power loss. As we know, the inductor in DC system is a short circuit. So there is no Q loss. So I don't need to have capacitor banks. I don't need to compensate for this. So that over long distances will, the longer the distance of the DC system, the cheaper becomes the DC until they reach a certain break point here. After that, the AC system becomes more expensive than the DC system. Now, this break point here is in hundreds of kilometers. So this is why the DC system is justified to be used in areas or in countries that have long distances. Canada is one of them. And we have DC system, as far as I know, in Alberta area. I think around 400 or 500 kilovolt DC system we have. Russia, China, US, India, all these countries, they have one thing in common, that you need to produce, to send the power for a very long distance. So it is justified. Also, DC system is justified whenever you have a link between countries of different frequencies. For example, in the Middle East, in the Gulf area, Saudi Arabia has a 60 hertz system. The rest of the Gulf countries are 50 hertz. And there is a project to link the two countries. How you can link 60 hertz with 50 hertz? The only way to do that is through a link, DC link. So you have 50 hertz from one country, change that to DC using rectifier circuit from AC to DC, and then change the DC into AC using an inverter to 60 hertz. Also, countries like Brazil in South America is the only country that has a 60 hertz. The rest is 50 hertz, so you need to do that. Japan is the only country in the world that has both 50 and 60 hertz. So inside Japan, you need to do that. You use a lot of DC systems there. Okay, so DC equipment now, especially insulators, is a reality. So we need to test those DC equipment. Okay, and this is why we need to have DC supplies. Now, the most efficient way, the most common way to produce DC is the full wave. This is the first one, half wave rectifier. So if I have an AC here, this is plus, minus, plus, minus. Okay. So in the plus, the diode is forward bias. So this will pass. The positive cycle will pass here. We'll see it here. And when you go to the negative cycle, the diode is reverse bias. Okay. So you will not be able to conduct. So that negative cycle will be cancelled. So you will have positive, positive, positive. Now, when you have a capacitor here, this will smoothen the instead of having just half cycles, you will have the voltage will look something like this, and then goes up and goes like this. Why this is happening? Okay, let's see what will happen. During the positive cycle, the diode is basically forward bias, and you will be supplying your current. So you'll supply this until you reach the peak here, and the capacitor will be charged, fully charged. Now, once you start to go to the negative cycle, this will be reversed bias. So this will be an open circuit. Now the capacitor will start to discharge. When you charge the capacitor during the positive cycle, in the negative cycle, the capacitor will start to discharge through the load. And this rate of discharge is depends on the what we call the RC time. But depending on the load, depending on the C, the value of the C, you will have faster or slower discharge. Okay. And this will lead to something that we call the ripple. Okay. Because the DC will not be constant, it will have some ripples. Okay. And the ripples delta V is equal to 1/2 V max, the maximum value you could have, which is this one, and this is the minimum value. So the difference between the two. And obviously, you don't want to have the ripple as high, you want to have the ripple as low. Okay. So as per the IEEE standard, this should not exceed 3%. The ripple factor you have should not exceed the 3%. Okay. So now during one period of t, we want to find the charge Q. We know that the current I is equal to dQ by dt, the rate of change of that charge. So the Q basically is the integration of the I dt. So if we have a load, we want to find the charge, how much charge is there that transfer to the load. So the Q is basically the integration of the current. Okay, the current is basically is VR, the voltage at the load, divided by R, Ohm's law for I, and hence your Q equal to I, the current, times T. T is the period, or 1/F. That is the amount of charge that you will have in your system. Okay, so your Q is equal to I divided by F. Now suppose that at any time the voltage of the capacitor is basically V and decreases by only dV. So it was V and reduced by dV during delta T. So the charge delivered by the capacitor during that period, now we know that Q equal to CV. This is the major relationship between the charge, capacitance, and the voltage. So if I'm talking about a delta Q only, so it's C with this dV. So I need to have transferring dQ to compensate for that dV. Now, so the voltage, when the voltage change from V max to V min, okay, the charge delivered by the capacitor will take the integration of CdV from V max to V min, and that is the integration of your charge. Now, if you substitute here, we know that the charge equal to, so from this integration of dQ is your Q equal to C of V max minus V min, and Q is equal to, so we know that if you go back here, when we define delta V, okay, is equal to 1/2 V max times V min. So it means that V max minus V min is equal to 2 times delta V. Okay, so that's explain this formula. From where we get this formula here, that we take this out, so we'll have 2 delta V. Now, so your delta V is equal to Q over 2C, and we know that the Q is equal to the IT. So your delta V is basically equal to the I, the current that's supplied by your generator, divided by 2 times the frequency times the capacitance. And then here, this is the testing DC supply. This is 100 kilovolt DC supply based on half wave rectifier. Okay, and now here we can see that from the previous equation, which is this one, basically here, that the delta V, which is the ripple factor, which I want to minimize it, is a function of the current, how much current the load will take from me, and also the frequency and the capacitance. So the load current, this is one factor that affect the ripple factor, and also the circuit parameters like the frequency and the capacitance. Okay. So to have a high voltage and as much as pure DC, you have to have a very, very bulky quantity, something like this, very, very bulky. Okay. Now, how to reduce this? Then we use the full wave rectifier. This is instead, now this will reduce the ripples because now during the positive cycle, this diode will be on faster and coming back here. During the negative cycle, this will be the one that is basically going on. Okay, so and coming back here as well. So you will have a better ripple factor when we use the full wave rectifier, but still the size problem is still there, and this will lead us to the solution of using the voltage doubler. Okay, now I will pause here. We'll have like 10 minutes break, and then we'll come back and we will continue. Okay, so now we talk about the doubler circuit. Let me again go back here and let me try to explain it. And this is like the fundamental of the doubler circuit is basically basics of electronics, something that you studied long time ago. So I'm not sure if you still remember. So I thought, okay, let me just go back to the fundamental. So assume that we have an AC supply here. I will start with the negative cycle. Negative, positive, negative, and positive. So we start with the negative, basically. So this becomes plus and minus because the polarity now reversed. So now when it comes here, this diode will be forward bias. Okay. So it will be forward bias. The other diode will be reversed bias. So this will be going this way and will be charging the capacitor as such during the negative cycle. Okay. Now, during the positive cycle, now this becomes plus and minus. So this diode will be now forward bias, and this diode will be reversed bias. So this will become an open circuit. Okay. So we have here the voltage V, and we have the voltage here V. So that capacitor will be charged by this V and that V, which is 2V. So you will have here 2V out. That is why we call this circuit a voltage doubler. This is a very simple way explaining this. And that is the Cockcroft generator. This is the basic fundamental DC supply, and it's based on this doubler. So we will have cascaded stages. Each one will give me 2V, 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 2V. Then I can basically have the voltage that I want, depending on how many stages that I will have. So that is as simple as that. What is the voltage doubler here? Now there is a software called PSEM. It's a free software. I might also share it with you. You can do a lot of simulation. This software is basically mainly for power electronics. It has certain limitations because you will have the free version, but it's good enough. So in here we showed you the voltage doubler. So basically we start with an AC voltage. It's V3, the red one. So the AC, the red one is your input voltage. What we are interested is the V4. V4 is the blue one. So you see here the voltage goes up here every time because you do not fully charge the capacitor from the first cycle. You will charge it a little bit every time until you are reaching to around the 4 kilovolt. So the big value was 2 kilovolt here. after some time, which is not that long, you will reach to the 4 kilovolt. So this is the voltage doubler, only one stage. Now, because the voltage here, the voltage at the across the diode here, it's VD1, which is the red one. VD1 is 4 times more than the or double the voltage, 2V. The diode should be able to block that voltage. What do we mean by that? Let's again go back to the fundamentals. So this is the diode. If you are to draw the VI characteristic of the diode, okay, so it's like this. So this is your V, this is your I characteristic, okay? So at around, let's say 0.7 voltage, the diode will start conducting. This than 0.7, there is no voltage. It's not yet, you don't have enough voltage to make the diode conducting, okay? Now, if you go to the other side, you apply here the negative voltage here, this plus minus, the diode doesn't conduct, it's an open circuit, okay? But that's not for infinity. The voltage in the reverse bias, it can withhold certain voltage. After that, you will have a breakdown of the diode. So that is the breakdown voltage of the diode. So you want to make sure that when the diode is reverse bias, it can handle this 4 volt or 2V, double the voltage of the supply. And here it's 4 kilovolts. So you have to select a diode, not just good into forward bias, but also you want to make sure that this diode doesn't break as we basically going in the reverse bias. Now, based on this area, we use the Cockcroft generator. In the Cockcroft, it's basically a multiplier. So that is, if you look here, this is your the voltage doubler. So basically, we cascade it. And this is how it look like. So all these diode cascades, okay, you have them here. I'm planning also to make another video because we have very similar supply here at the high voltage lab. So I will make a closer look to the stages of the DC supply, and I will share it with you hopefully later on. So that Cockcroft voltage multiplier circuit is this can supply 300 or even more. We have the one that we have here, plus minus 300 kilovolt. Now, to get a negative voltage, you need just to do an arrangement. So basically, you have to remove this and bring another one. You're just reversing the diode direction, but you cannot have the same setup to give you plus and minus. You have to switch in the for the capacitors. Okay. So you start from a single supply here, and you get, based on these doubler effects, you will get the voltage of your interest. So let's again, I did some simulation on a 3-stage diode multiplier circuit to again give you some sort of insight about what is going on in each one. So here, basically, we have here during the negative cycle that there will be open circuit. So D1, D3 will conduct during the negative cycles and open circuit in the positive cycle. So your D1, we have seen that in the negative cycle it will conduct, in the positive it will not. So D1, D3, D5, which is basically here, your D5, and so on, it will be conducting. And here is the voltage across these diodes. And this is your input diode. On the other hand, V2, V4, V6, those will conduct during the positive cycle. We have seen the D1, D2 in the positive cycle, it will conduct. Same thing, D4, same thing, the D6, and so on and so forth. And these are the voltages across them. Now, this is a 3-stage multiplier. This is your input. This is your V1. This is your input here. Now, we measuring the voltage across this. This is VC2, which is this one, VC2. You see it here, stabilize around, going for around 4 kilovolt after some time. So the voltage here peak is 2 kilovolt. So each one is less than 4 kilovolt because of the loading effect. Ideally, each one will give you 4 kilovolt, but practically it will be less than that because of the current. So now we have the voltage across each of these loads. Now, if we come and see at the end how it will look like as an output, that will be your output V7. And your V7 here is coming close to the 10 kilovolts, something like that. And you saw the ripples. These are the ripples, and here is the current. Now, those supplies, they have a very, very limited current capacity. Okay, and to be able to deliver high current, you have to have a bit of a different design. But again, what we are testing here, we are testing insulation. So it's expected that the current will be less. Now, this is the final formula for delta V. If you remember, we have it as I over 2FC. Now, you add how many stages you have here. So this is the formula for your ripple factor. And you can see here, as you increase the stages, they are increasing the ripple factor. As you increase the C, reducing the ripple factor, increasing the current, it will increase the ripple factor, and so on and so forth. And the voltage, that the maximum voltage is 2 times N times V max. V max is the peak value of your input voltage. So that's enough for the DC. And let's now move to the last part of today's lecture, which is the impulse testing. Now, we start with the lightning impulse voltages. Lightnings, it hits overhead lines, and there is no control on lightning. And we'll talk about later on about switching. Switching, we have a control. We know when we'll do the switching. But lightning is something that we don't have any control over it. Now, when a lightning hits a transmission line, it will inject tens of thousands of ampere. Now, because the surge impedance of the overhead lines is in the range of hundreds of ohms, you will have a very high voltage across the insulators, bushings, cables, and so on and so forth. Okay? And hence, now the actual wave shape will vary, but people came up with a standard waveform that will be using it to test those insulators, and that is the same waveform used by the IEC standard or the ANSI standard. And this is, we call it the 1.2 by 50 lightning impulse waveform. This has been ANSI standard for, and also it's the same as per the IEC standard. So what is the 1.2 and what is the 50? 1.2 is the rise time, and the 50 is the fall time. What is the definition of the rise time and the fall time? We will see in the coming text. Okay, so here we generate that in the lab. So we have a waveform that rises in 1.2 microsecond, but we'll see how we will specify the 1.2, how we will measure the 1.2 now. Now, you come and look here. The starting of the waveform is not linear. And this is due to the reason how the impulse generator works. And I will talk about that later on. So remember this, that the starting here is not linear. Okay, and that will make it hard for us to decide the starting of your impulse. Okay, so for that reason, now we will have something called the virtual front. Okay, now what is the virtual front? The virtual front, basically, which is the 1.2 microsecond, you come here at 0.3 of the value of the crest, and 0.9, and you draw a straight line between the 0.9 and 0.6, and whatever intersection with the x-axis, that is your virtual start. So you basically measure everything from that virtual start. So you're starting 1.2 microsecond and your 50 microsecond, and based on this. Okay, so what is the rise time and what is the fall time? The abscissa of which is O1, the one I just talked about, this is the line going through the 30 to 90%. So now I decided the starting. Now your T1 is equal to 1.67 times T90 minus T30. That is your T1, and this is should be the 1.2 microsecond. Okay, the fall time is the time between when the waveform basically reduces to the 50% of the value minus the original, the virtual origin. So that is how we define the rise time, the 1.2 and the 50 microsecond. Of course, it's impossible to get exactly 1.2 microsecond or exactly 50 microseconds. So we will have some tolerance as per the IEC standard 4. IEC standard 4, this is the standard for high voltage testing. So most of the equipment requirements are stated in IEEE standard 4. So the big value, for example, if I want to have a voltage 95 kilovolt impulse, okay, then it is acceptable to have that plus minus 3%. For the virtual front time, which is this one, it's plus minus 30%. For the virtual time of the half value or the 50 microsecond, you have that a plus minus 20%. So that is the lightning impulse. We have another form of lightning impulse called the shoved lightning impulse. So in the shoved lightning impulse, what happens? You basically have the rise time as it is regularly, and when the signal or when the waveform reaches between 2 to 5 microseconds from the starting, okay, you shove your impulse to have a very steep discharge. Why we do that? Okay, we will talk about it in details later on, but if we have a bushing, this is one way of why we use that. We use something we call arcing horns to protect the bushings from the high voltage transient. So basically, if a high voltage hits there, you like a transient, you don't want the energy to go through the transformer. You want to take the energy outside. Okay. So basically, when it hits here, it will go here. This is an open circuit, but when it reaches certain level, okay, this will conduct. And the whole energy will go through the arcing horns to the gap or the ionized gap to the tank to the ground. Okay? So that will mimic this type of discharge. It's very, very severe because the dV by dt here is extremely steep, and this will put a lot of stress of the insulation. So especially, for example, for pole-mounted transformers, we have to test them against pole lightning and shoved lightning as well. Switching is something also very, very important. Okay, so we need to also test the equipment under impulses or surge voltages that mimics switching events. And these are some examples about how much over voltage we are getting at different scenarios. For example, if you have an infinite bus as a source with a trapped charge on the line, and we do some switching, an open-ended line, you'll get up to 4.1 per unit increase. So the voltage has increased 4 times more. And here, these are some examples with typical values. And every time the voltage is going beyond, higher than the rated voltage. So we need to test the equipment under these conditions. For that, we will have an impulse waveform, but the characteristic of it is different. We said that for the lightning, it's 1.2 by 50 microsecond. So the rise time is very, very sharp, and the fall time is a bit slower. Here for a switching, that again mimics the reality of a switching impulses. They are slower. It's 250 microsecond for the rise time, 2,500 microseconds for the fall time, with these tolerances that you will have in the fall and in the rise time. Now we use the same generator, but we change the resistors, as we will see. By playing with the resistors of the impulse generator, we can basically change the rise time and the fall time of your generator. So it's the same one we call Mark's generator. We'll talk about it later on today, actually. So it's the same generator, but I'm just playing with the resistors. We can change the rise and the fall time of the impulse waveforms. The final one, we have the steep front waveform. Now, these steep waveforms, we have extremely fast signals. So here, this one, it has 1 kilovolt per nanosecond. And here it is 4 kilovolt per nanosecond. So the rise time here, it goes very fast in a very short period of time, in nanoseconds. There, the rise time was in microsecond. Here, it's much faster. Okay, and why we do that? Now, for high voltage composite insulators, we use this to detect if there is any defect in the internal structure. So when we use very fast waveforms, we will not have a flashover from outside because of the way the arcing happens in air. I can explain that in brief, but there is another course we talk about dielectric materials in details. But let me explain a little bit of how the failures happens in air and why we need to go for very fast impulse waveforms. So again, let me go back here. Okay. So if you have high voltage from one side here, I would just try to oversimplify it. Actually, this is much more than. Okay, now why an avalanche? Why an arcing happens? There are different mechanisms. One of them is the Townsend mechanism. Basically, when you apply very high voltage, there will be some free electrons here. Okay, and this electron, once you apply very high voltage, it will be energized. So it will multiply basically an atom. So this will result in two electrons. Each one will hit another atom. So you will have more electrons until you have the avalanche. Okay. Now this process takes some time to find the electron that will initiate the process. Now, the faster your stress is there, the more likely that you will not have this electron. So you might increase the voltage without basically finding the electron to start the avalanche. This is why when we test, for example, 13.8 kilovolt transformer, if I test it under AC, I test it at 38 kilovolt. If I test it under impulse, I test it at 95 kilovolt, much higher voltage. Why? Because to start the breakdown under impulse test, it will take longer, higher voltage to be able to start the avalanche compared to when you have a slow signal. As I said, this is like oversimplifying it, but this is just to explain you the idea of why when we have very steep front, you will not, this is to avoid any external flashover. And if there is basically an internal defect, then it can be detected without having an external flashover. And you can see here, as you increase the steepness, you will need higher voltage to have an external flashover. So for example, here, if you use 1 kV per nanosecond, this is the voltage around 350. If you increase it a little bit more here, it's much higher. So this technique, we don't use it too many, but if I want to find the internal defects of an insulator, we use this type of test. Now, the final thing we want to talk about today is how to design the generator. We talked about transformers for AC, DC supplies, and now the impulse generator. This is a one-stage generator. Basically, what we do, this is an air gap switch. It's not a switch that you close and open by yourself. This is an air gap that will break down and connect the circuit. At the beginning, this will be an open circuit. You close the switch, you charge this capacitor C1. Okay, and then once this is fully charged, you trigger that this air gap to have an arc. If it has an arc, it closes the switch. If this is closes, this switch will be open, and whatever you have here, the charge on the capacitor, it will be discharged through the C2. C2 is your object. This is the object that you are trying to test. R1 and R2, basically, are the resistors we use here to shape our signal. Is the front and the fall of the signal. This is as I said, we have two parameters, the rise time and the fall time. So R1 will decide the rise time and R2 will decide the fall time. Now there are certain criteria here for the design of the impulse generator. So C1 should be much larger than C2. R2 should be much larger than R1. The energy here is 1/2 CV squared. The efficiency of the output is C1 over C2 plus C1. And the output voltage will look like something like this. This is the impulse, the function that represent a rise and a fall. It is a double exponential functions. Now R1 is around 50 ohms, R2 is around 1000 ohms. So let's have a try to play with these parameters, fixing the others. So for example, here, this is an R1, this is an impulse, okay? And we see the impact. What is the impact if I increase R1? If you increase R1, basically, you are making the impulse slower. So this is more suitable for lightning, and this is for switching. Okay, so by playing with R1, I can increase the rise time. Now for the fall time, it is R2. Okay, this is the impact of R2. So if I want to have something very that goes very fast, I use, for example, 100. If I increase this to 1000, so this is the way is the full time. If I want to have it even more, then I keep on increasing R2 as well. Okay, so how we make a generator? We don't use one stage because one stage is not practical. Let's say if I want to test the samples at 1 million volt. Okay, so usually every stage can provide you with 100 kilovolt, usually. Now, Marx in the early last century came up with a very brilliant idea. In a very simple way, you charge the capacitors in parallel, discharge them in series. As simple as that. So if I charge all the capacitors in parallel, for example, if this is 100 kilovolt, and this is a typical value for the DC supply from the input, if each one is charged charged at 100 kilovolt, so you will have here 100, 100, 100, 100. If you discharge them in series, then how many stages? You multiply those stages by the voltage in a single stage. Okay? So that is how you get your voltage. Now your R1 here is the one that decides the front, the rise time. R2, which is this resistance, will decide your tail. Now here we have these air gaps are our switches. Now this is again a visualization of how this is happening. So that is the charging here. Here you charge, and here you discharge. When you charge, you see here all the capacitors are charged in parallel. Those air gaps are open circuits, so you don't see them here. Then when you discharge, those will be conducting. All of them will be conducting. The capacitors will be actually in series here. So they will be like in series. So the voltages, you just add the voltages here. And each one, whatever V you have, that's your output. So this will be like multiplying the stages by the voltage at every stage. Very simple, but very brilliant idea. And since more than 100 years, around 100 years, this is still the technology we use in our impulse generators. Now, there are some generators that are solid state. Instead of having an air gap switch, we have power electronics switch, but again, the same idea. Now, why we use air gap? Air gap because they are very, very fast. You want the switch to close in a very, very fast way. There's nothing, no switch in power electronics is faster than a breakdown of air. So that is the whole idea why we use this. Now, in the charging stage, we charge across R. R, those are the resistors R, to have a sort of balanced voltages. Now, the discharging happening through R1 and R2. Now, in the first stage, how to ensure that you will have uh, arc here. Only in the first stage, we have one of the circle is a hollow here, and it has inside a trigger rod. And this is called the trigatron spark gap. So basically, we trigger this with a pulse. So we increase the voltage here, and we said that the flashover to happen on the arc, it depends on the availability of the electrons. Okay. Now, when we trigger this, we are ensuring basically that this will trigger because we have high voltage and a trigger switch to generate those electrons, then you will have the flash. Now, the reason that we start with this switch will start closing, and then the other switches in a very short period of time will come after that. This is why when we look into the starting of the impulse, it's not linear. It starts like this and then goes up. So those switches, they don't close all of them at exactly the same time. You start with the first stage and then cascading, it, they will start. Okay. And now here we will have a voltage, let's say V. Now, once this is charged and this is closed, the voltage here will become equal to 2V. 2V meaning that we keep the same gap between all the switches. So if this is closed, a breakdown happen at V. When this switch to V, definitely this will arc as well. And as you go higher, you will have higher and higher and higher voltage because now we have the voltage from the supply and from the capacitor before that. So you have higher and higher stress. So now we are sure that every time we will have higher voltages, so all the gaps will be closing. Okay, so we need to control the closing here. Okay, but the others, because of the very high stress happen multiplied at each stage, those gaps will follow one after another. And this is why, yes, this happens in a very short period of time, but still it will take some time until all of them are basically are triggered. Now, we don't have R1 and R2 as just one resistance. That's not practical. So what we do basically, we distribute them. We have R1 and R2 instead of having one bulk resistance as summation of those resistors. So this is your R1 and this is your R2 as well. This is how the impulse generator look like. Okay, so this is a 3-stage. These are the air gaps basically here. This is the one that start the trigger. This is the high voltage DC that you charge them. Okay. Again, I will try to make a video, close video from our generators in the lab to show you all these resistors as well. Now, what is this? We'll talk about that later on. This is basically to measure the voltage. We'll talk about that next week, actually. This is your R1. This is the one that connect between your generator and your load. This is 1, 2, 3, 4, 5, 6, 7, 8 stages. Each one is 100 kilovolt. So we can get up to 800 kilovolt output from your generator. Now that is the old generator at the University of Waterloo, but now we have a much newer one. And as I said, I will try my best in the coming few days, trying to make a video for you to show you this. Now, so these are the components. We have the capacitors that we are charged. Those are oil-filled capacitors, and they have to have a very low inductance. Why? Because the system is capacitive. If we have high inductance from the capacitors or from the leads, so again, in the leads, we use flat copper strips to, again, reduce the inductance. If you have high inductance, you will not be able to have something like this. This is called first order system. First order system. It's only capacitive. If I have an inductance there, then my impulse will not look like this. It will look like this. There will be a lot of ribbons, a lot of charging and discharging. These ribbons is because of the interchange of the energy between the capacitor and the inductor. Or even worse, you can have something like this. You don't want this. This is not a good impulse. So we try to minimize our inductance from the leads, from the capacitors, anything there. We try to minimize the inductance. Now, of course, we have the gaps. They have to be able to to deal with high heat, because of when arcing happens, there's a very high heat there. So you want to make sure that you don't damage those arcing spheres. Also, you have a motor control of the air gap. Now, the air gap, you control it so that you can control at what voltage you want to charge the capacitor. Maximum is 100 kilovolt, but maybe you want to only have 50 kilovolt, okay, or 60 kilovolt. Let's say I want to have 120 kilovolt as an impulse. Each stage can give me up to 100 kilovolt. So I have two stages, each one is 60 kilovolt. Now, when you apply 60 kilovolt, the air gap is different than when you apply 100 kilovolt. So this is usually controlled by a motor. Finally, safety is extremely important in the high voltage lab. So again, I will make a video for you for our lab. Fences all over, physical barriers. You cannot keep these high voltage equipment like that. So there are always fences around them. Also, there is an interlock everywhere. In every place you go in high voltage lab, there is an interlock. What does it mean, an interlock? That if someone go inside, you cannot energize the system. Okay. Once you open the door, you disconnect the system. So that's also one of the precautions to make sure that no one is getting harmed. Grounding sticks is very important. The rules of thumb here, if your transformer or generators is not working, you have to ground them. Always. Only take the ground when the system is about to be used. Warning signs, lights also has to be everywhere there, so that there will be everyone will be aware. Especially if sometimes you are running a high voltage experiments, so you have to make sure that there is clearly identified that there is a high voltage going on there.